In this lab, I'm going to lead you through implementing derivative and integral control into your slider motion. We're going to start out with the proportional control that we ended with last time. Start by making sure that your Kp value is a float rather than an int16. That was an error that I made in the last video and told you about in class. But if you missed that, start by making sure that this Kp line is a float. Now, when we implement PID control, we have to have proportional control to start with. But after that, whatever additional types of control we implement is up to us, and adding additional kinds of control can either make the response better or make the response worse. We can use proportional control all on its own if that gives us the best response. Or we can try adding on derivative control and do PD control, that is proportional with derivative. Or we could not add on the derivative and add on the integral instead and have PI control. Or we could use all three and have full proportional integral derivative or PID control. Which type of control you use depends upon what kind of a system you're trying to control. If you take a class that is about controls, you will learn how to determine which type of control you can use mathematically by modeling the system, that in this case your slider, and figuring out by solving equations which type of control you should use. But in practice, you can also do this by the guess and check method, as long as your system can be tested without damaging any property or people. In our case, in lab, our little slider can be tested without damaging anything, so we could figure out what kind of control to use experimentally just by trying something and seeing what happens. The best way to do this is to actually design an experiment. In this experiment, we'll change the kind of control we use: proportional, proportional integral, proportional derivative, or full PID control. And we can also change the values of the gains, such as Kp. Our output, or our dependent variable in the experiment, will be the properties of the time response, the overshoot, the settling time, the steady state error, and so forth. If we keep track of the output for each value of our input, the independent variables, we can experimentally figure out the best way to control our system. So in this lab, we're going to start by implementing derivative control and adding that onto our existing proportional control. Now, in order to implement derivative control, the first thing we need to be able to do is measure or record the derivative of the error. The derivative of the error is the change in error. In order to record the change in error, we need to have a variable not only for the error, that is our error right now, our current error, but we also need to remember what the error was the last time through the loop. That will allow us to calculate the change in error. So we need to have another variable up here. And I'm going to call this new variable last error. This will be the error that we had the last time through the loop. I need to start this out being something, because the first time through the loop we won't have a last error. So our code will not run unless we give this last error variable some value to start out with. Now, every time we go through this loop, before we go back and do it again, we're going to take the variable last error and set it equal to error. That way, when we get back up into this loop the second time around and we recalculate the error, we'll be able to remember what the error was last time. So let's calculate the derivative of the error. The derivative of the error will be equal to the current error minus the last error, and all of that has to be divided by the amount of time over which this error change has occurred. And that amount of time is approximately equal to the amount of time that we delayed through the last loop. So I'm delaying by 1 millisecond, so I'm going to divide this by 0.001 or 1 millisecond. Now I haven't declared this variable derivative yet, so I'm going to go back up to the top here and I'm going to declare that as a float, that is a value that will have a decimal point. So we'll have a float derivative. Now, in order to use derivative control, in addition to calculating the speed as Kp times error, I'm going to add on Kd times the derivative. Now I also haven't declared Kd, so I need to go back up here and add a float Kd. And we need to set that equal to something. I'm going to set it equal to 1 for now. Let's go back down to where we are using this right here, and let's think about what the effects of this Kd will be. Let's imagine that the slider is approaching its target position. When the slider is approaching the target position, the value of error will be less than the value of last error. That means that the value of derivative will be negative. Since Kd is positive, that means that this whole term, Kd times derivative, will be negative. The effect is that when the slider is approaching its target position, the speed will be reduced by the Kd parameter. In other words, the faster the slider is approaching its target position, the more the slider will slow down from the derivative component of the control. That's why derivative control is said to add damping to the system. It will damp out the oscillations by making the speed of the motor slow down when it's approaching the target position too quickly. On the other hand, when the current error is greater than the last error, that is, when the slider is moving away from the target position, the speed will be increased by the derivative. In other words, this will cause it to move back towards the target position faster than it would have otherwise. We need to go down and put this same two lines now also in the other case, in the else case. The last thing we need to do here is to check and make sure that our value of Kd makes sense. The way we do that is by thinking about what will be the value of derivative when the slider is making a motion that is typical of its motion. For example, let's suppose that in one iteration of the loop, the error has decreased by, say, 100 digital value. In that case, the value of derivative will be 100 divided by 0.001, or 100,000. If we leave the value of Kd at 1, that means that we'll be increasing or decreasing the speed of the motor by 100,000 just because of the derivative effects. That's way too much. We actually want to increase or decrease the speed by maybe tens, not by hundreds of thousands. So let's go back up to KD and make it a more reasonable value. So now we have the right order of magnitude for KD, but we still don't know exactly what value it should have. For example, if we made this 0.0002, that will change the speed by 20 when the error is 100 more in one iteration of the loop than it is in the last one. So do an experiment on your own. Set KD to a value like 0.0001 and run the slider. Look at the rise time, the settling time, the overshoot, and the steady state error. Then change the value of KD, say to 0.0005 or something like that, and see how the parameters of the time response change. By doing several of these experiments with different values of KD and KP, you can find the values of these two gains that give you the minimum rise time, the minimum overshoot, the minimum steady state error, and so forth. Lastly, let's implement integral control. Integral control is a value of the gain, Ki, times the sum of the error. So the first thing we need to do is take this value of Ki and add it up here as one of our gains. Once again, we'll start it out at 1.0, and later on we'll figure out what order of magnitude is reasonable. We also need a value called error sum. I'm going to add this up here as an int 16. And once again, I'm going to set it equal to 0 initially. Now, every time we go through the loop, I'm going to take the value error sum, and I'm going to set that equal to what it was previously plus the current value of the error times the amount of time that we had through the loop. This will numerically give us a value for the error integral. So consider what will happen as we go through this loop. Every time we go through the loop and the error is non-zero, the error sum will add up over time. The more the error adds up, the greater the integral component of the speed becomes. This will help us to eliminate steady state error over time. So let's see if we can figure out what would be a good order of magnitude for the value of Ki. Every time the value of error is around 100, the value of error sum will increase by a value of 0.1. So in the value of speed, the error sum component might be around the order of magnitude of 0.1, a decimal. In order to have that have an effect, we might want to have Ki be a value around 10 or so. So let's start out with Ki being 10. Do an experiment where you run the slider, the motion of the slider, and Measure things like the rise time, the overshoot, the settling time, and then change the value of KI to a different value and see what are the effects of that different value of the gain on your slider positioning.